Hello and welcome back. This is presentation 5.4 of the binomial probability model, a special case of a random variable. And note at the bottom here we have a few acknowledgements. These are the objectives of this presentation. Please feel free to stop the video at any time and jot these down. We want to look at the postulates of this model, and we ask you to think of the example of tossing a fair coin. It consists of n trials or tosses from a population. The second postulate, on any trial is only two outcomes, heads or tails, success, failure. On any trial or toss, the probability of success is generated by P, which we label as P of X. And in this case, probability of the heads equal to a half. Outcome on any trial is independent of the outcome of any other trial. Tosses are independent of each other. And we're interested in the number of successes or heads in the number n trials. And for experiments such as this, the mean and standard deviation is given as n times p. For 100 tosses, probability of a head is a half. We can expect 50 heads. The standard deviation or variability is plus or minus 5, about that mean. Now, to put this in perspective, we want you to look at the case of a general numeric random variable. We have to look at this table and compute these two special cases, the mean and standard deviation. But in the case of a binomial random variable, n equals 100 trials, in case the probability of success may be 20%, then we can say the mean is n times p, standard deviation is given here. Translated, that means that n times p is 20 successes in 100 trials, and the standard deviation is calculated to be sigma equal to 4. Now we're going to apply that to the case of genetics, perhaps Mendelian genetics, where a certain gene trait occurs 1 in 3. Probability of X then is 1/3. And a random sample of 6 items is selected. And we want to look at the possible outcomes. And look here, we're putting in these formulas here. To get 0 successes means they're all O's. Each probability has a probability of 2/3. And here we have it 2/3 to the 6. To get 1 X and 5 O's, here we have the 6 ways of doing that. There's 6 choose 1 ways of getting 1x from 6 times 1/3 to the 1 represents 1x, and 5 failures or O's is 2/3. And just labeling these here, and just feel free to pause the video and go through these. 2 x's and 6 o's, 6 choose 2, 1/3 squared, 2/3 fourth. And putting the rest on the screen here. And again, feel free to pause the video at any time. 5 successes, 5 x's, 6 choose 5, 1/3 to the 5th, 2/3 to the 1. And finally, we have probably 6 successes. Now the total of those should be 1, which it is. And now the mean or expected value is coming on the screen here. We need this column. And going down here, the total of these is 2. So going the long way, the mean is 2, but using the binomial formula, it's also 2. The standard deviation is given by this formula here, and this is given by using this x squared p of x column over the far right. We have that summation is 5.33. And here we have the 5.33 minus 2 squared, which is sigma x p of x, giving a standard deviation of 1.155. Using the binomial formula, it turns out to be the same value. This justifies the use of this binomial formula. This means we can expect on average 2 x's in the 6 over the long run, but this can vary by as much as plus or minus 1.16. Now we're going to look at the case. Now we want to look at the case where we have 25 animals in the north. It's expected that 20% of the herd is infected, and we take a sample of 25. We find that 11 animals have this infection, and we want to look at the likelihood of this happening. Here's the probability distribution of X based on n equal 25, p equal to 0.2. Here's the distribution, and you can see here expected value somewhere in this range. And here we have, using the binomial formulas, we can expect 5.0 animals of the 25, 20% of 25 to be infected. Standard deviation is 2. And if we have X 11 animals infected, finding the Z-score is 3, and 3 of course is way up in the right tail here, the likelihood of that happening is quite rare, and this tends to support the notion that the infection rate has increased. And that's the end of this presentation. We ask you to take notes and go to presentation 5.6.